At 4:36 a.m. on August 21, 2017, dozens of massive commercial vessels navigated the narrow shipping lanes of the Singapore Strait. Among them was the USS John S. McCain, an 8,000-ton guided missile destroyer. In this high-traffic zone, the bridge crew attempted a routine transfer of steering control. Instead, they became disconnected from physical rudders and throttles, locked out by a touchscreen interface. For decades, marine engineering relied on direct mechanical linkages. When an operator pulls a heavy lever, steel cables and hydraulics move physical mass. Modern architecture severs that mechanical link, inserting a layer of digital abstraction between human intent and the machine. Replacing tactile hardware with software layers introduces invisible points of failure. A poorly designed user interface or a single line of bad code can paralyze the physical capabilities of a multi-billion-dollar military asset. The origin of this vulnerability dates back to the mid-1990s. The U.S. Navy launched the Smart Ship program, an initiative to reduce crew sizes and operational costs by replacing mechanical failsafes with automated commercial software, specifically dual Pentium Pro PCs running Windows NT 4.0. The primary testbed for this digital integration was the USS Yorktown. During training exercises in 1997, the ship's entire network was disabled by a single keystroke. A crew member troubleshooting a fuel valve opened the machinery control system. Inside the remote database manager, they entered a 0 into a blank data field. The software lacked basic input validation. It attempted a divide by zero operation, triggering an arithmetic exception and buffer overflow that crashed the database. The network lacked error segregation. The failure rippled across the interdependent network, severing connections to critical nodes, including propulsion control. The guided missile cruiser's engines stopped entirely. A warship equipped to track hundreds of airborne targets was left dead in the water for nearly 3 hours. Stripping mechanical resilience in favor of commercial off-the-shelf software introduced a lethal fragility to the fleet. Simple logic errors now dictate physical reality. 2 decades later, digital abstraction deepened. By 2017, the fleet was rolling out the Northrop Grumman Integrated Bridge and Navigation System. This design mandated the removal of traditional, tactile mechanical throttle levers. In their place, engineers installed flat, feedback-less touchscreens. The implementation bypassed established military standards for human-machine interfaces. It ignored MIL STD 1472, the protocol requiring visual segregation of critical errors and physical distinctions between controls. A fatigued bridge crew needed to split steering and acceleration duties while transiting a high-traffic strait. Rather than moving a physical switch, they were forced to navigate through opaque, nested digital submenus. Digital interfaces without tactile feedback strip operators of spatial memory. In high-stress maneuvers, an operator looking at a flat piece of glass is operating blind. On the bridge of the USS McCain, navigating these submenus resulted in a precise mechanical error. The crew accidentally triggered a digital command that unganged the port and starboard thrust controls. This schematic shows the physical state of the ship at that moment. The helmsman believed an emergency override button had transferred physical steering control to the aft compartment. In reality, the digital interface had merely returned the local helm to a manual backup mode. Sensing a loss of control, the commanding officer ordered a speed reduction. The operator pulled back the digital throttle. Because the shafts were unganged, this action only slowed the port shaft. The starboard shaft maintained high RPM, forcing the ship into a sharp left turn. The 8,000-ton destroyer veered out of control and directly into the path of the Alnick MC, a 30,000-ton oil tanker. 10 sailors lost their lives in the collision. In the aftermath, the U.S. Navy ordered the removal of touchscreen helms across the destroyer fleet. By reverting to mechanical joysticks, the institution admitted that digital abstraction is a fatal liability. The vulnerabilities found in shipborne software are mirrored by the digital infrastructure resting on the abyssal plain. Submarine communications cables operate upon the foundational physics of optical transmission. Data travels as light, confined within a silica core by a lower refractive index plating through total internal reflection. This cross-section details the evanescent wave. Electromagnetic boundary conditions dictate that a fraction of optical energy penetrates the boundary and decays outside the core. Intelligence operations exploit this. By microscopically bending the fiber, technicians siphon leaking photons without disrupting the main data stream. The fundamental properties of light create a mathematically undetectable backdoor into the world's most heavily armored data networks. The origins of deep-sea optical tapping trace back to the CIA and Navy's declassified Operation Ivy Bells. In 1971, the USS Halibut located a Soviet communications cable in the Sea of Okhotsk. Divers installed an inductive tapping device that mirrored the unencrypted military communications passing through the line. The modern synthesis of this mechanical engineering and optical espionage is the USS Jimmy Carter, a nuclear submarine modified for seabed warfare. During its construction, the Navy spent an additional $887 million to insert a 100-foot extension known as the multi-mission platform. This section functions as a dry, pressurized underwater splicing chamber. Utilizing specialized fore and aft thrusters, the 12,000-ton vessel can hover perfectly over commercial cables, pulling them inside the hull to install Evanescent wave couplers. From a bridge touchscreen to a subsea cable, global stability now depends on the behavior of photons leaking from glass threads on the abyssal plane.